A new water treatment plant opens while the older pumping network outside it keeps losing pressure. The contradiction began in the funding, not the pipes. Construction received one protected project budget. Upkeep must compete again every year. The first answer, building and operating, draw from different funding horizons. So postponing maintenance frees resources now and reduces capability later. That makes deferral resemble borrowing, even though the obligation appears as weaker service instead of recorded financial debt. The structure rewards visible capacity today, while sending much of the repayment to future users. Consider a bounded regional water utility. One newly built treatment plant feeds an older pumping network that still carries water to customers. The plant arrived through a dedicated construction project. Pump servicing comes from an annual operating budget, competing with every immediate service need. The director postpones a scheduled pump overhaul again, keeping the current operating budget flat and preserving resources for visible demands this year. Water still arrives, but pressure failures summon emergency crews. The postponed work returns as a larger capability loss rather than a line of debt. The funding split is the mechanism. Construction receives a discrete decision and a defined project horizon. Operation faces repeated allocation choices after opening inside this utility. Project funding is committed before the facility exists. Operating resources are reconsidered while the system already works, and other demands are already visible during each cycle. That timing makes deferral attractive to the operating director. The release technicians, parts and cash solve present problems immediately. Deterioration remains delayed for the moment. The new plant makes capacity visible. Successful maintenance is quieter because its achievement is a failure that does not occur inside this scenario for current observers. So the maintenance gap can emerge from the budget architecture itself. Each decision looks defensible nearby, while future capability erodes across the system over several cycles. The borrowing analogy begins with a transfer. Postponement releases present labor, components, and operating capacity by drawing against the system's future performance across budget periods. Repayment arrives through weaker pressure, emergency work, reduced throughput, or earlier replacement. The future system returns resources that the present system consumed during later operation. But this loan carries neither a fixed principal nor a scheduled interest rate. Its eventual cost depends on where, demand, alternatives, and interruption timing inside this scenario. Repeated deferral can deepen exposure. A skipped service changes the condition inherited by the next budget cycle, making another postponement more consequential for future operators. The crucial reframe is that an unchanged financial balance can conceal a growing operational obligation. The liability sits in capability inside the equipment, not accounting entries. The analogy holds where capability moves across time. Current users receive service supported by maintenance resources that future users will have to restore through later maintenance. The analogy breaks where repayment becomes uncertain or uneven. A machine may keep working, fail abruptly, or impose its cost on different people across the network. Money debt can be refinanced before payment. Lost service cannot always be recovered after the interruption has already reached a household or workplace during the outage. Planned maintenance also differs from emergency repair. The first can fit around operations. The second arrives when the system has already lost flexibility inside the station. Deferred maintenance is therefore an implicit, conditional loan denominated in future service. The borrowing language clarifies timing, while uncertainty limits the comparison across different outcomes. Now separate the decision makers. The construction team is judged on delivering the new facility. The operating director manages service after the opening throughout the scenario. Construction resources are attached to a defined asset. Operating resources remain contestable because they must cover changing needs throughout the working system after the opening. Each manager can act rationally inside a narrow horizon. One completes the commissioned asset, the other preserves the most urgent services this year within assigned responsibilities. Together, those sensible local choices can leave the existing network progressively less dependable. The gap belongs to the structure, connecting the decisions over successive cycles. This is the system-level payoff. Individually defensible allocations can produce a collective maintenance gap when their horizons and consequences remain separated across the utility. The distribution starts with present budget holders. Deferral gives them flexibility to protect immediate service, staffing, or emergency capacity during the current cycle inside the scenario. Future operators inherit the pump's changed condition. They face fewer easy options because later operation begins after the earlier maintenance window has passed. Users absorb weaker service, while emergency crews absorb compressed repair time. Neither group controlled the earlier choice that released the resources during the failure. The new facility delivers visible capacity immediately. The older networks avoided failures would have benefited people later, making the two benefits arrive differently across the horizon. Deferral becomes especially attractive when the chooser receives today's flexibility, while another party carries tomorrow's service loss and repair burden inside this structure. Change the horizon and the incentive changes. A single party responsible for construction and long-run operation can compare both sides together over the asset's life. A dedicated upkeep reserve can also protect future service, but it reduces present flexibility. The gap closes by accepting a different current constraint during that period. Funding maintenance beside construction can expose whole life cost before opening. It makes the future operating claim visible during the initial allocation before service begins. Yet protected upkeep is not free. Technicians, components, and cash held for future service cannot answer every present demand within the current cycle. The practical rule is precise. The gap narrows when future service value enters the same decision that allocates today's construction and operating resources over the shared horizon. But postponement can be rational. A pump nearing planned replacement may not justify a full overhaul if its remaining task is small and flexible before replacement arrives. Declining use, easy substitution, spare capacity, or minor interruption consequences can make deferral cheaper than restoring capability that will soon become unnecessary inside the scenario. The borrowing analogy remains limited because physical consequences are uncertain. A postponed overhaul might matter little, or it might meet an unusually costly failure during later operation. Test the boundary with a lightly used auxiliary pump already scheduled for replacement. Its service can shift temporarily to nearby spare capacity during the transition. Skipping that overhaul preserves resources with little capability loss. Deferral behaves like harmful borrowing only when the future sacrifice exceeds the present value released over that transition. Support conditions create another boundary. Modular pumps, local parts, and flexible crews can reduce the future cost that follows a postponed service window. A critical specialized pump with thin support creates the opposite result. Delay ties a larger future capability loss to the same present saving during the outage. The refined claim is conditional. A maintenance gap matters when separated decisions systematically omit future service losses that outweigh today's released resources over the relevant horizon. We can now resolve the opening contradiction. New capacity and declining upkeep can coexist because their resources are approved through different processes and horizons inside one utility. A postponed overhaul transfers labor, components, and attention from future reliability into present flexibility. It is an allocation across time, not resource disappearance between budget cycles. Repayment appears as service quality, emergency effort, constrained choices, or replacement pressure. That is why the obligation can remain financially invisible inside the budget. The maintenance gap is therefore a structural time horizon problem before it is a story about individual carelessness. The process can generate the pattern over time. The gap tends to open when construction funding is protected. Operating resources are repeatedly contestable. Consequences arrive late and different parties absorb them. It tends to narrow when one party sees the whole horizon, compares life cycle demands, and directly carries the service risk created by deferral. Ownership can change this comparison by changing who controls resources, who captures continued service, and who pays when the system becomes unreliable. This analysis does not prescribe a spending level. It identifies which costs a funding design makes visible now, and which costs it sends forward. The full answer is that financing design decides whether upkeep competes as a recurring expense, or enters the original long horizon capacity decision. To test a long-lived system, ask who funds construction, who funds upkeep, how often each decision reopens, and when service consequences appear. Then trace who receives today's released resources and who inherits tomorrow's weaker capability. That distribution reveals the incentive to defer. The maintenance gap explains why upkeep slips. It leaves the next question: who sets the price of continuing after switching becomes difficult? A system's future depends on whether its funding horizon lasts as long as its service horizon. The future is just incentives at scale. See you tomorrow.